Hello everybody. In the previous video we have learned about the torque acting on a planar coil when the plane of the coil is inclined at an angle to the magnetic field. In this video we are going to learn about the moving coil galvanometer, and initially we will start with the construction of the moving coil galvanometer, and here what I have drawn is a western type moving coil galvanometer, and this one is used in our physics laboratories. So let us start by each and every part one by one. Here I have shown a scale. So this is a pointer which reads the reading on the scale, and this is a horseshoe magnet, and with the horseshoe magnet I have attached two concave pole pieces, you can see. So one of them is the north pole, the other one is the south pole, and then we have a cylindrical core. So I have not mentioned it here, but you can write it down. This is a cylindrical core. Cylindrical. Soft iron core. Here. So this is a cylindrical soft iron core, and then there is a coil which has been wound over it, but initially we have taken a metallic frame, then putting the copper wire over it, which is obviously laminated. So this is how we have put it over here, and I have tried to make something for you so that you can easily understand. So assume that this is a soft iron core and this is a frame. So obviously it is there in the lower part also. So then you will start winding the copper wire over it, and there are large number of turns, and then there are two free ends of the copper wire, one from where you started and the other from the end where you concluded winding it. So these are the two ends, the ends which I am just now talking about. So one of the end has been connected to the positive terminal of the battery and the other has been connected to the negative terminal. Then there is a pivot. A pivot has been connected to the core, and it is almost like this. And then with the pivot there is a pointer. So if this will move, so the pointer will move like this, right? So this is the basic construction of a moving coil galvanometer. Now, when we open the galvanometer in the lab, so what is it that we really see is that the two concave pieces are almost there as I have drawn over here. Then the coil which I have just now shown you. So this is the coil. Now one end, this is the first end of the coil, this is the second end of the coil, and this is the axis of the green line is the axis of the coil. Then the axis of the coil is actually pivoted between these two ends. This is a pivot in which the wire has been fixed so that the axis can move if this rotates. Okay, so it is almost like this. This is the axis and a wire is there, so the axis can rotate like this. Then we have two hair springs. One is here and the other one is here. Both of them are made up of phosphor bronze. Phosphor bronze. These are hair springs. So one, and this spring, the shape of the spring is like this, like jalebi, right? So this is the shape of the spring. So one end of the spring is connected to the axis here, and the other one is connected to this point. Similarly, for the other hair spring also, one end is connected with this part here and the other one is connected to this, and the rest of the things I have already told you. Now, so this is the construction. Now what we really want to do here is, what is the principle of working of a galvanometer? Now the principle is that whenever there is a current carrying coil in the presence of magnetic field, it will experience a torque. So principle has already been discussed earlier in the previous video also as a complete derivation. that torque is experienced by a coil, and the torque was equal to M cross B, where M is Ni into A. N are the number of turns of the coil, I is the current that is flowing through the coil, A is the area. Area means length into the breadth of the coil. Then it has been taken as the cross product with magnetic field, so cross with B. So this was the torque experienced by the coil. Now, you might have also seen the relationship which we did with the plane of the coil making an angle alpha with the magnetic field. Now, when we talk about this relationship, this was NIAB sine theta, where theta is the angle which normal to the plane of the coil makes with the magnetic field. But we have also done the relationship in which we have taken the angle which the plane of the coil makes with the magnetic field, right? Plane of the coil makes with the magnetic field, and that angle we took as alpha. And in terms of alpha, when we wrote torque, it was equal to M B cos alpha. So instead of sine theta, we have cos alpha. So this is another way of expressing torque. So always remember, when we talk about angle between normal to the plane of the coil and the magnetic field, we express it as NIAB sine theta. When we take the angle as plane of the coil making an angle alpha with the magnetic field, we express it as NIAB cos alpha. So now these are the two expressions. Just remember these two, and I am just erasing them. Now after the principle, you really have to understand how does it work. So what happens is that when current is passed through the coil, here, the torque is experienced by the coil, right? So the torque is experienced and the coil wants to rotate. Now, because torque always produces a rotational motion, so the torque produces a rotational motion, and therefore the core inside, it also rotates. Then the pivot, which is holding the pointer, that also moves, and we get a reading on the scale. Now, this is the working of the moving coil galvanometer, but you can see that I have drawn another diagram over here which is showing these black lines. Then I have shown the concave pole pieces here. I have also shown the phosphor bronze here springs, and we have not yet discussed what are these for. So one by one I am explaining why have we considered all these things. Okay, so number one, up till now you have understood that the torque experience can be written as MB cos alpha due to the current that the coil carries in the presence of the magnetic field. So first expression is this. Now what will happen is that when the coil will rotate because of the torque, just see this diagram. When the coil will rotate, this hairspring and this hairspring, one of the hairspring tightens itself and the other one just unfolds. Both of them are adjusted in such a way that one of them gets tightened and the other one just opens up more. But since it is happening, and therefore they will try to apply a counter torque in order to bring the coil back to the original position. So there is a torque because of the current and the magnetic field, but what will happen, you have to understand is that if the pointer suppose goes like this and there is nothing to stop the pointer, then the coil will keep on experiencing the torque and the pointer will keep on moving. But somewhere the pointer has to stop. So there has to be a counter torque that has to be applied on the coil so that it will stop moving. And for that purpose, these two hairsprings, they start acting. So they apply a counter torque and when the torque applied by these springs is equal to the torque which is experienced by this coil, at that time the coil will get fixed in one position. So it will remain like this, right? And beyond that it will not move further. So at that time what we say is that there is a counter torque which is applied by the hair springs, and that is proportional to, that counter torque is proportional to alpha. Alpha is the twist that the hair springs have experienced, because either they have been tightened or they have been loosened. So one of them has been tightened, the other has been loosened a little bit, but the twist obviously is the same in both of them. So the counter torque is proportional to the twist produced, which is alpha. And we just remove the proportionality sign by putting a constant. So this becomes K into alpha. And just now I have said that when this torque becomes equal to this torque, at that time the needle comes to a particular rests on a particular point on the scale, and this coil rests in a particular position. So this has to be equal to this. So it means that we can write down MB cos alpha is equal to K alpha. Now M can be written as NIA into B cos alpha is equal to K alpha. Further, I can write down I is equal to K alpha divided by N, A, B, and there is a factor of cos alpha here. Now, you can see that current is equal to all these things. K alpha divided by N, A, B cos alpha. Now, K is a constant of proportionality, so the value is fixed. Number of turns you have fixed. Area of the coil you have fixed. B is the magnetic field that has been fixed. The only thing that varies over here is alpha, because there will be a particular twist in the spring. So if alpha here, suppose here alpha is changing by 1 unit, then all these things are fixed, so current will change by the same unit. Now alpha changes by 2 units. Suppose the twist is double the previous one, so current will change by double the value. So it means that both are directly proportional to each other, but we are also able to see a factor of cos alpha here, which will not let current vary linearly with alpha. Means that it will not happen that when twist is 1 unit, current is increased by 1 unit. When twist is double the previous one, current has to be double to make this twist. But because of this factor of cos alpha, it will not let it happen so. But whenever we have to measure anything, we really need to have a linear scale, in which when one thing increases by 1 unit, the scale also increases by the same amount. So we really want to get rid of the factor cos alpha, and that can be easily done if alpha is 0 degrees. Now alpha 0 means cos 0 will be 1, so this factor will not be there. So it means that this factor should not be here, cos alpha should not be here, it means cos alpha should not be here. So we really want that cos alpha should be 1. Now in order that cos alpha is unity, alpha has to be 0, which means that what was alpha? It was the angle that the plane of the coil makes with the magnetic field. Now we really want that at every time when it rotates, at every time the plane of the coil is making an angle of 0 with the magnetic field. Now if the magnetic field is like this is the north pole, this is the south pole, and you have a coil which is moving inside, so this will not happen. It will have certain angle with the magnetic field when it will start rotating. But if we create a radial field, which has been shown here with the help of the concave pole basis, then obviously the alpha angle becomes 0 at all the points of rotation, at all the angles, at whichever position the coil is, the alpha angle is 0, and which makes cos alpha as 1. So what is the final result? that in order to have a linear relationship between I and alpha, we have taken a concave concave pole places for radial magnetic field, and therefore we get the relationship as I is equal to K upon NAB into alpha. So cos alpha has become 1. So I have explained the use of each and every part over here. Always remember that there are two hair springs which provide a counter torque, and also remember why do we use a concave concave pole pieces so as to provide the radial magnetic field. Now one thing I really want to tell you here is that initially when the moving coil galvanometer was designed, it was not like this. The one I have shown over here. Now this is a very handy instrument which we can use in the lab. But initially when it was designed, the construction was a little bit different. And I will just draw a small portion over here so that you may understand how the construction of galvanometer began. So initially what I have drawn here was not like this. Initially when it started, it was like this. So there was a torsion head here. This is known as a torsional head. Then along with the torsional head, there was a phosphor bronze strip, and this is a concave mirror. So this is a concave mirror, and here you have a phosphor bronze strip. Then after this phosphor bronze strip, the rest of the arrangement is same. Okay, rest everything is same. Now what was the arrangement other than this? In front of this, so you have this arrangement, and the coil was obviously attached here. Here the coil was there, then there was a spring fixed with this, then obviously it was there inside a container, right? That was a non-metallic one, and the whole apparatus was kept like this. Now when the coil used to turn, the concave mirror also used to turn. Then there was a lamp and a scale arrangement in front of it. So the light used to fall on the concave mirror, it reflected back, then there was a point on the scale which used to tell us what is the reading, and that with the help of that we could identify that how much current is flowing through the galvanometer. So this arrangement was a very difficult one to be handled by the students, because then the lamp and the scale arrangement has to be fixed all the time at one place, so that it may not happen that you are taking the reading and some things have moved from their place and then you are not getting the accurate reading, because otherwise also galvanometer detects the presence of very small amount of current. So if there is a small error in our experiment, we will not be able to do that. Therefore, instead of using a suspension with the help of which the phosphor bronze strip, with the help of which this coil was suspended, now we have done a pivot arrangement. So pivot arrangement is like this. Pivot arrangement is like this. This arrangement does not allow the coil to move any ways other than the rotational motion. So this is a kind of pivot arrangement. So the coil is there and the axis can move, but it will not go at any other place other than this. Good. So this is how it happens, and in the lab, as I've already told you, we use a moving coil galvanometer, which is a Western type, but it started with the suspension type moving coil galvanometer. Hope you all have understood it, and in the next video we will start with the current sensitivity of the galvanometer and the voltage sensitivity. We'll also learn how to convert a galvanometer into a voltmeter and an ammeter. Thank you. Till then.